First of all, thanks for inviting me to Mike's Fest, and this has been really good fun for me, and I wish I would have come before to more theoretical physics conferences, because it's really interesting to talk to people here, and there should be more of stuff like this. And I should say Mike is the person who brought some sort of machine learning for physics people to the AITP conference, to the Artificial Intelligence and Theorem Proving conference. So if you are at least a bit into these topics, then please join our crowd. You will see that we are friendly and happy to engage mathematicians and physicists and discuss with them how is it that you can do science and the machines cannot. I will, because Christian already gave a lot of the setting, I may sort of skip over quite a lot of the propaganda and just go very quickly to the demos. But let me just sort of try to say something about the general plan here, which sort of is captured by, to some extent, by this picture from a famous book about the life of Bertrand Russell called Logicomics, which I definitely recommend to anybody who wants to learn about the sort of revolution in the foundations of math that happened in the beginning of the 20th century. So there is this dream which is sort of attributed to Leibniz, but like there were crazy people even before Leibniz, to sort of have mechanical means how to resolve all sorts of disputes. Like his example is like some accountants who just compute, and they, because they can compute, they can compare their results and find the mistakes and find out who is right. And his dream is to extend this to everything, right? Like to all of math and physics and like law and Russell, who was one of the people who was very much involved in this process of bringing mathematics to sort of formal symbolic level, was sort of very much inspired by this dream. And like here they say, like, what does it mean that you didn't achieve Leibniz's dream? And I would say a lot of what we are doing, and people before us were doing, like Hilbert, etc., is inspired by this crazy dream that goes back such a long time. And like we don't know like what it takes, but like especially with all these combinations of learning and the formal setting where we sort of can basically play some sort of game, like with Go and with chess. You can play a game and you can learn from the rules. And what the formalism gives us is a similar, much more complicated game that sort of involves all of math, basically. And if you believe that physics can be embedded into math, then all of physics, right? Or at least some parts of physics. So that's the sort of current approach to my approach to this dream. And this is the slide where I sort of repeated. So when we are doing math and science, we do a lot of deduction, a lot of like complicated like reasoning chains where we apply one modus ponens after another, etc. But we also learn from what we are doing. Like we find patterns, we have a lot of knowledge, and we sort of learn how to steer through. We learn how to create new concepts, new abstractions, etc., etc. And like one way how to sort of start to emulate this on computers is to take these big libraries of formal mathematics, which are today like reasonably big, as you already heard from Christian, and at least try to sort of learn how to play the game there. Like if we learn how to play the game there, then it's already like a crazy big success, because some of the theorems that have been formalized, and I guess you will hear from Patrick, are becoming really like research level math today. So just achieving this would be really very interesting thing. And another funny picture from this book that I really like. So many of you are physicists, and what I should say like that happened as part of this process of bringing mathematics to formal foundations was that people like Hilbert, who were the prophets of the new era, were met with a lot of resistance from people at least as good as Hilbert, like people like Poincaré, who sort of wouldn't buy into it exactly like for this reason, that they sort of saw and couldn't sort of grasp the mismatch between the very low-level logical layer on which like people like Russell and Frege and Hilbert were proposing to put math, and the way like he was doing math, like the sort of very intuitive. So like some of you might know this, right? Like he has this science and method, and he says that like mathematics isn't just deduction, right? And what does it mean? Like he may mean like all sorts of things by induction, like the thing that we call conjecturing today, or like really generalization from examples, etc., etc. And like I'll just mention one more guy. Like so in some sense, like from let's say physicists, and quite often from mathematicians, like in like most of the last century, we heard that like proving hard mathematical theorems, like you had people like Penrose who would even claim that there is some Gödelian reason while humans are better than whatever AIs or computers, and have to be better. And the interesting person in this sort of debate is Turing, because like he is the guy who basically proved early in the 30s the sort of Entscheidungsproblem, the sort of the halting problem, and its sort of extension to undecidability of things like any reasonable mathematics. You cannot have a terminating algorithm that will tell you whether a theorem is provable or unprovable. Like this is the line of destruction that sort of was unleashed upon the Hilbert's program of doing all this, like having all these series of mechanic procedures for deciding more and more mathematics. But like Turing himself, like during the war, went into a lot of statistical AI, you could say today. He basically defined the AI field in his 1950 paper, where he defines the Turing test, and where he brings all these reasons to the sort of naysayers why computers can think, like what does it mean that computers can think, and why he doesn't see any of the objections like that, for example, came later from people like Penrose, that computers wouldn't be able to sort of learn these things that humans are doing. And what's even funnier, that in this like sort of foundational AI paper, the last chapter is on learning machines. So if any of you think that machine learning is some recent 2015 craziness, like read 1950 Turing, where he basically, in some sense, if you sort of stretch it a bit, he sort of predicts the AlphaZero thing, like this sort of self-learning, playing chess and learning from that. So I'll skip a lot of this. So you sort of heard from Christian already some bits about like what is formal mathematics. So it's this process started for real with Frege, but Frege had bugs in his logic, got destroyed by Russell. Russell did it for real, then it was too complicated, so there was like a series of refinements of the logical foundations, ending up with, I don't know, some reasonable set theory, type theory, lambda calculus, high-order logic, like all these are some sort of valid foundations for formal mathematics today. And I would say another funny remark is that the first AI program, or like at least if you read into the history, is actually a theorem prover by Newell and Simon, this logician theorist. And again, like today's impression of what, if you ask a person on a street what is AI, they will tell you it's deep neural networks, right? Like when AI started, it was like logic theorist. And so when these these people who sort of put math basically into symbolic logic also invented computers by some sort of accident, like Turing defined the universal Turing machine to show that it cannot do something basically. So it's like a theoretical construction initially, but then actually they started to build them, right? Everybody knows this. And on top of that, like in the 60s, people like De Bruijn, and then creating Automath, and then Robin Milner and Andrei Tribulec and other people in the 60s and 70s started to really take this seriously, say, well, what prevents us to really have a lot of mathematics formally expressed and proof-checked on computers? And the field sort of went on, and for a long time it was sort of in this battle with mathematicians who sort of didn't believe it in the same way as Poincaré didn't like Hilbert. So that's sort of one branch of this like trend, like started basically by Frege, and then the other, like even the sort of more AI trend is this automated theorem proving, like again, like starting with this logic theorist basically, where mostly in the 60s, but already in the 50s, people really started to think about, like, can we use these computers to get proofs of complicated mathematical conjectures, theorems? And it's sort of a pretty old classical part of the AI with all these systems like Otter, Vampire, Ishpas, and Prover9, etc. And a lot of that sort of didn't succeed in some crazy way, but there are sort of limited successes. So for example, SAT solving, like propositional theorem proving, is today, you can say it's superhuman basically. If you have a problem in propositional logic, you can do with these systems systems really crazy things. Like they are extremely well engineered. The heuristics there are very, very good. Like improving them by some deep learning is near to impossible because of how good are the sort of high level heuristics there. And people actually use them for proving some like very combinatorial discrete problems today. So what I started to do long ago for my master thesis is to basically do this, like take some piece of formal mathematics and try to learn how it is done. So at the time I used something called inductive logic programming, ILP, which sort of, if it works, which is hard because it's sort of combinatorial search, it sort of gives you explainable rules of how the mathematicians are doing their proofs. So I think that sort of failed or didn't work for all sorts of reasons at the time, but it looks like in the combination with the like strong statistical machine learning methods, people are sort of coming back to this today, and I can really show you some examples. Why do this today? Like there are, I guess Patrick will talk about it, and Christian also said something. So people really formalize interesting theorems. So like probably the canonical example for some time is Tom Hales's proof of the Kepler conjecture, which was an open problem for 400 years. Then Tom and his student proved it in 1998 using a lot of computation basically, and the proof was not really easily checkable by mathematicians. And they basically failed. They said like, we cannot 100% review and proof check this. So Tom decided to do it fully formally. And like after some like we started in 2000, so maybe 10, 12 years, the proof was actually done in the Hall and Isabelle systems. So it's like I would say the most impressive example for mathematicians. But there are many other today. So Georges Gantier did this Phi-Thompson theorem in 2012, and his team, which is like two graduate books in group theory. And people do all sorts of like industrial verifications, like they verify a compiler like this CIIRC or an operating system microkernel, etc., etc. So it's really industrially the technology is becoming sort of mature, and then there are all these crazy AI visions that I already mentioned. This is so my colleague in the Netherlands, Freek Wiedeck, wrote more than 10 years ago, more like 20 years ago, a comparison of the different proof styles of proof assistance. And he starts with this like very simple informal proof by Hardy and Wright about the irrationality of square root of 2. So this is the informal thing that all of you saw. And then he sort of gives the example of the different formal proof assistance. So this is called declarative proof style, which was sort of pioneered by the Mizar system, where you sort of basically mirror the structure of the informal sort of natural language, natural deduction proof. And then what you saw from Christian is a very different proof style done in whole light, where you apply tactics. So this is sort of a proof script done in the whole light system. And this is something in between, something where you sort of combine the two things. When it's mostly declarative, but you have the power to use some longer tactical, like some sort of chaining of theorem proving procedures to help you to discharge the thing. So again, like this is a field that has been born like some 60 years ago, and people have done quite a lot of these things in various ways. This is the Kepler conjecture about the optimal packing of balls in space, and as I said, it's been proved by Hales. The proof was big, and if you look at these things, like this is actually formally written in whole light, so it says that if S is a polyhedron and C is a face of the polyhedron, then C is also the polyhedron. So one of the things we did quite early, like in 2014, was to take this relatively big corpus of like some 25,000 lemmas, and we showed that by relatively cheap machine learning methods, like this was like before the deep learning craziness, you can, like when you sort of combine it with the existing or mildly improved automated theorem provers, already automatically prove 40% of that thing. So that was like one of the good signs that like sort of these combinations of learning and theorem proving are meaningful and useful to the people who try to formalize things.
When you say this 40%, this is proving 40% of the lemma that have already been stated, not writing any statement? Or?
No, this wasn't doing any conjecturing. This is like what is called the hammering scenario. So that became popularized by Larry Paulson, especially in the Isabelle system. So you have a proof assistant, like in the canonical example, you have Larry Paulson's Isabelle, and you are typically working in some sort of more complicated logic than what your automated theorem provers can do. So you need some sort of translation that sort of takes the more complicated logic and translates it to the simpler logic. That's called a hammer, and the hammer also does other things like selection of interesting facts for proving your current conjecture in your proof assistant. And then you call all the automated theorem proving / AI technology, and if it gives you the proof, you sort of try to recover the proof in that sort of more complicated logic that you are working in. So this became, I would say, quite popular, and it's been sort of done probably in all systems but lean, I guess, gradually. So like I said, like in 2014-13, we had like 40-45% success on these like proof assistant libraries, and like with more and more machine learning put into like the automated theorem provers, we could do last year about 60% of the MISA library. So I'll show you some things about it. In general, like here is a bit of an overview, like what are all the ways how people have done some machine learning / AI combinations in the sort of theorem proving context. So you can do these very high level things when you sort of just learn how to select lemmas from the library that already contains a lot of proofs. Or you can do like very low level things like guiding an automated theorem prover that is doing really the very, very low level modus ponens style inferences, which is sort of expensive because the neural networks especially are very slow compared to the fast symbolic solvers. Then there is this very reasonable mid-level thing, which Christian was already showing, where you sort of guide some application of the blocks, of the reasoning blocks tactics that the humans already pre-programmed. So it's, in some sense, it's sort of cheating compared to the lowest level, because you sort of rely on the humans to sort of pre-create useful blocks, but it works, right? Like once the humans have done something useful, why not use it and support the humans even more? And then you can go like into this like fully AI scenarios, like theory exploration means that you get some initial axioms, then you have some sort of conjecturing system that tries to sort of develop this theory And as it proposes new conjectures, it sort of tries to prove them or disprove them, and maybe it's sort of slightly targeted in the sense that there is some ultimate conjecture in the end. So we almost cannot do that today. Or these feedback loops, like these sort of alpha zero star feedback loops that you sort of learn from your own successes and repeat that ad nauseum, are very interesting. And Christian already mentioned this auto-formalization, where we would sort of take, I don't know, archive or all the math and physics textbooks and turn them into a thing that the computer can proof check. So that's like a, that actually seems today more doable than I thought when we proposed it like 8 years ago. Okay, let's get to the demos. Let me start looking at the time. A very, oops, does this work? Can I copy? I probably need to do. Yeah. So this one is fairly simple. Yeah. Maybe I should give you a bit of context first. So we have a. I'm doing it wrong. Presentation. So we have this Enigma system, which is basically putting a lot of machine learning methods, starting from very fast ones to very slow and sort of AI deep learning ones, into like the state-of-the-art automated theorem prover called eProver. And we run it on a reasonably big corpus of mathematical proofs, like this sort of Mizar mathematical library. And we basically run this in this proving learning loop in many iterations. So when we sort of started it, when we finally got something that started to work, we ran the initial unguided, unmodified automated theorem prover, the eProver, in 10 seconds over the whole corpus of something like 60,000 problems. And it could prove about 15,000 of them. And then we trained the sort of, I don't know, neural networks. In this case, it actually aren't neural networks. These are gradient boosted trees, which are sort of much faster than neural networks and very, very competent. And put it into the theorem prover to guide the inferences, the choice of what inference the system should do. And then we ran it again, basically on the full library. And in the first iteration, like, we ran it in two different modes. Like, one is standalone, one is when we combine it with the original system. It can sort of improve the performance quite a bit. So it can add, like in this case, some 6,000 new theorems proved. And then we train it again, like on these new theorems, etc. And we iterate this, I don't know, about 6 times. And then in the end, we get a system that can prove like 70% more of the problems in the library in 10 seconds, like no cheating, no hiding of the neural network somewhere on your server, etc. in real time. So that was like the initial sort of priming of the sort of learning / proving loop. And then we sort of continued with that forever, for about one more year. And we were sort of doing all sorts of modification and doing it in all sorts of ways, from this 25,000 to like more than 40,000 I think now we have like 75% of the Mizar library, and like here is one program that is looking simple, but like we only got it when we started to do this. Like we couldn't get it before, and it's just proving the Pythagorean theorem in inner product spaces. So I'll show you the thing how it looks like in the human formalization. So it says like you have a real unitary space, you have 2 points or vectors that are orthogonal, and then you do the sum, you take the norm and square it, and it equals the norm of x squared plus the norm of y squared. And it's all like this human proof is doing everything that some I don't know, first, second year student taking the lecture about Hilbert spaces would be doing. So he expands the definition of orthogonality to be that the scalar product is 0. And then he says that the scalar product is always positive because of the definition of scalar product, etc., etc., etc. At some point, he uses the definition of orthogonality, and he concludes the final thing after doing a lot of these equations. So this is, I don't know, like 15-line proof done in Mizar by a human. And so what you want from the automated theorem prover at this point is like it sees the whole previous library at this point, which may be, I don't know, like maybe 20, 30,000 facts and definitions in the library. So you first want it to select the sort of good, suspicious statements in the library, like the definition of scalar product, etc., etc. So that's this sort of premise selection task. So in this case, it chose 342 out of these like 20, 30,000 by doing this sort of machine learning from the previous proofs that are already there in the library. And on top of these 342, you now start some inferencing process. So you want to combine them in such a way that you reach the conclusion. And that's a crazy combinatorial process that typically leads nowhere in most hard cases, and that's where the sort of machine learning guidance is helping you. So in this case, what I'm showing you is the automated proof, like found by this like learning guided theorem prover, which took something like 200 steps. So the final proof done by the machine in full precision, in full detail, is like, I don't know, 10 times longer than the sort of human proof that you see here, because the sort of machine found proof, the sort of proof that is found by the automated theorem prover needs to be much more detailed in various ways, though, because the proof checker has some sort of intelligence of its own. So you can, whenever you say that this follows from this by this definition, it has some sort of auto-completion properties, and it can infer a bit by itself. So that's where you get the blow up between the sort of low-level thing where you really need to finish the proof perfectly, and the human level thing that gets partially auto-completed. What would be, yeah. So that's the final thing. So let's say it takes like 200 steps, and out of this 340, it only used for the proof 34. So that's also interesting. Like you have some approximate intelligence telling you, like, from the 20, 30,000 that were preceding this formula, I am guessing that these 342 might be good for the proof, but it's still very approximate, and the real proof takes only 10% of that. So that's what you reveal only during the process of actually doing the proof and finishing the proof. And the whole thing took about 4,000 iterations of some theorem proving loop where you always choose the new fact to infer with, and you sort of do inferences with the things that you already decided are sort of the good facts that you should be inferring. And during this process, you generate something like 60,000 facts, all of that in about 30 seconds. So these are how these machines work today. Like, they generate quite a lot of stuff. On the other hand, like, if you, for example, compare it with the machine learning architectures, these are relatively small numbers. So if you, for example, look at what like Christian was saying about transformer, if you see how many like layers and how big are the layers and how big is what one today calls an inference of these large architectures, these are small numbers compared to like 1 billion parameters in the transformer. But it works sort of fairly differently. So that's at least one example to introduce you to this sort of stuff. Let me see if I want to show something more. Yeah, maybe this one is interesting. So almost like at the end of this loop, we also ran a version of another theorem prover, Vampire, which is like even stronger than eProver because it has more heuristics in it. And in a long time, in 500 seconds, it could prove this. Let me see if I can. Maybe I'll click the Wikipedia thing here. It could prove basically this. So when you have ordinal numbers in set theory, well, actually it's this one. So you have the first ordinal number called epsilon 0 that is like the fixed point of exponentiation of omega. So if you do omega to that ordinal number, you get that number. And the Mizar proof is really on the level of being fairly non-trivial. So here you see the Mizar statement, and on the left-hand side you say, give me the first epsilon ordinal number that is bigger than 0. And on the right-hand side you see this sort of tower of exponentiations, like omega to omega to omega. And the proof is non-trivial to say the least. Like, it's not totally impossible, but it takes quite a while to the human formalizer. And the Vampire proof. So in this case there is some statistics about it. So it takes 73 formulas. It only needs 49 of them, but the proof is like 1,200 inferences long. So it's like, I don't know, 6 times longer than what I was showing you before for this Pythagorean statement. It does 40,000 iterations of this basic inference loop, and it generates like more than 2 million clauses. And what is quite interesting here, this is again a neurally guided, very cheaply neurally guided architecture, where the neural guidance, because it was done in a very smart way by Martin Sura, by my colleague, takes only 20 seconds. And most of the problem solving is done in SAT solving, because the problem can be split into many components by SAT solver, by propositional solver. And basically, what the neural model is doing is trying to say, like, this component is easy, this component is easy, this component is easy, and then sort of combine the results from the components into the like full foolproof. And another big part of the problem is congruence closure, which is sort of equational reasoning. So, and we couldn't get this proof with the standard architecture. So for example, here the sort of component splitting, like the fact that this theorem prover can sort of automatically split itself into many cases, and many of them are easy and some of them are the relevant ones, plays a big role here. So it sort of also demonstrates that you sort of need these combinations. You need these algorithms that take care of the combinatorial part of the problem. Like very often that helps you a lot. Like in the same way as I said that the SAT solvers are today superhuman in solving like the sort of discrete combinatorial problems, doing architectures that sort of combine such sort of superhuman combinatorial capability with the sort of human style learning with the neural was sort of essential in solving this problem. So I'm almost out of time as usual. So I'll So one thing to show you for the conjecturing part is this. So it sort of I guess what Christian said was that today you can use things like transformers or recurrent neural networks or whatever to create conjectures. So some 2 years ago, I basically ran the sort of standard GPT and trained it over a big corpus of bizarre theorems and proofs. And basically, then I was looking at like what new theorems I can generate with it. And one interesting thing that happened was that in this case, when you have in the library, you have a theorem for finite groups, it in a very simple way, just by omitting the finiteness, the transformer generalized it to arbitrary groups, which was actually beyond our capability of theorem proving at that time. So we couldn't automatically prove it, like our AI TP systems were too weak. So I asked algebraists, and they sort of confirmed that this is actually something that they give to the students as a not totally trivial proof in some first or second lecture on group theory. But it sort of shows you, like I guess what Christian was talking about, that at least to some extent, like in this case, it's very simple. You are just playing with adding or removing assumptions. You can use today's neural technology to generate conjectures that are sometimes interesting. And here's another one. So I was asking the system to prove that sequence is increasing on that interval, and the GPT decided to conjecture that every differentiable function is increasing. Good try. So these conjecturing things, they sort of split the problem into two, right? Like so in this case, if you already know that this is true, then proving that other thing is easy, right? But proving that this is true is sort of not gonna work for you. And maybe the last demo that I'll show you is this one. Tebault, so in general, like this conjecturing and synthesis of interesting mathematical objects is really like one of the tasks that we do not know how to do well. So Tebault Gauthier, who is this guy who did a lot of interesting things recently in this field, has spent his recent life working with the integer sequences. So he has this system that is neurally guiding synthesis of programs that explain integer sequences in the online encyclopedia of integer sequences by Neil Sloan. And here I gave it a bunch of primes. Tebault, by some sort of neural guidance combined with some sort of learning of the semantics of the programs, basically running the programs on the first integers, learns to synthesize more and more complicated programs, recursive functions, etc. Like he has a sort of domain specific language for that, which is not totally readable. Well, in this case, it is quite readable. What did I do wrong here? These are not primes, it is 25. Okay. I need to do more. Let's try again.
How does it know to match with some sequence from the library, or not to just do some polynomial interpolation, for example?
You mean it could do just if then else, like on the
Let's try the polynomial which passes through this.
It's
how does it know it should match it with integers, for example?
it's sort of discouraged to cheat. You could say that, for example, if you gave it like the first 10 primes, it would come up with if then else statement saying, well, if the input value is 1, then return 2. If the input value is 2, return 3, etc., etc. But that program is actually longer than the program that Tebault generates here. So this is the program for quote unquote primes that he discovered here. So the guiding heuristic for synthesizing these things is Occam razor, basically, to have the program as simple as possible, because then you believe that it sort of generalizes, right?
But how does simple is defined? How is simple defined?
Yeah, in the domain-specific language. So for example, you do not have real numbers available. You have only numbers 0, 1, and 2, I think, and then you have some operations on top of that. So doing like some polynomial over real numbers would be expensive for him. So here, the program that he synthesized in Python looks like that, and you might think that these are primes, but actually they are not, even though I was really telling Tebault forever, like, please invent the primes for me. And what the machine did in this case is Fermat's pseudo primes. And the OEIS is designed in such a way that it's almost impossible to invent primes, because the pseudo primes differ from the primes only somewhere on this position, the 3, 4, 1, and the primes are in OEIS only up to position 58. So you don't see the 3, 4, 1 here, the first difference to pseudo primes. But what we did to overcome this evilness of fate was to try the characteristic function of the primes, which I believe is this one. No, maybe it cannot. Let's see. And it can do this one. And the sort of fairly interesting thing is that none of us understood why this invented function defines primes. Like, we needed a mathematician to tell us that it's actually based on something called the Wilson theorem. Which says something about how you characterize prime. So the point, and I'm almost finished here, is that like this system in my mind is some sort of way forward from these crazy memorizing models that do not compute. They are not Turing complete. They do a lot of statistical reasoning, like the RNNs and the transformers. But like this system is like one of the first approaches for generating like recursive functions, like the things that are not typically too much in the world of the statistical neural machine learning people, but are very much in the minds of the mathematicians and the programming people, like writing some Fibonacci sequence, etc. And combining it with the sort of statistical guidance for synthesizing these objects, and maybe like gradually leading to even some combined architectures that, for example, you will have a neural network that has some like symbolic execution, some sort of computing or reasoning bit in it that will help it to do the tasks that are like very hard for the purely neural systems today. So I think I have eaten all of my time. So the rest of the slides is for the next talk. And if you, as I said in the beginning, we have a friendly conference, this AITP, that is actually happening this year again in France in September. And Mike is our valued co-chair, taking care for AI, TP, for physics. And happy birthday to you, Mike, and I hope that you will have as much fun as we all have doing all these things, and that you will evangelize all these physicists here to come and conquer physics by machine learning, theorem proving, and artificial intelligence. Thank you.
Any questions?
Yeah, very nice talk. I mean, your automatic systems at this point tend to, when they work, they generate longer proofs. And I wonder, have you looked much at taking a proof that works and shortening it or simplifying it to automatically do that?
Yeah. So there is this effect that Christian already mentioned that really appeared for the first time in my PhD thesis in 2004, that you can really find many shorter alternative proofs from different premise selections, and this has really appeared throughout the history many times. So that's one thing, like just playing with the AI system that selects the facts from the library. And I even, like 10 years ago, when I had the first system working over MISAR, because I'm reviewing the MISAR submissions to the library, I wrote a system that for me, as an external reviewer of some MISAR formal article, runs the system over it and tells me that this proof could be shortened. And then I look very smart telling the author whom I'm reviewing, this proof should be shortened. So it's like, for me as a reviewer, that's sort of AI made me look smart. The other thing was actually this proof that I was showing from the vampire world. So I think it might have been this one. Yeah. So so this one, in this first run that we got it, that Martin Sura got it, took 500 seconds. But for example, we have methods like that again predate like the deep learning. It's some sort of symbolic regression methods that generate suitable strategies for these automated theorem provers. And if you play with various combinations of these components that the complicated theorem prover is doing, then he can reduce this to 10% of the running time. So it's not that the final proof would be much shorter. The final proof is sort of similar, but instead of generating 2 million redundant clauses, you only generate, I don't know, 500,000 redundant clauses. So the systems that we do are in some sense very often motivated to produce short proofs, because we run the systems with time limit, and we want to get more and more of the harder and harder proofs. And I guess a big thing of what is happening is that the machine learning becomes smarter and smarter in like learning how to do the boring part that it already knows how to do, and focusing on the new parts that it still doesn't know how to do. So I would say the compression of the search is somehow implicit in the task. But I would need to look at examples to sort of prove to you that I'm right. That I can also give you the opposite reasoning. So we have systems that are guided symbolically, and some people like Bob Verhoeff are proving open algebraic conjectures with them. And they work by symbolic matching of the lemmas in the previous proofs. And I have the experience that when this works, it sort of can guide you to the goal by a very, very long way. And if you do things in a brute force way, you will get a much shorter proof by an unguided theorem prover. So the brute force has the advantage of going wide and possibly short. The smartness in this case can take you very long and give you a long proof. So it's to contradict myself. You can do both. Yeah. It's complicated.
What is semantic AI?
So one example from 2008, when I wrote one of this first system for premise selection, for this feedback loop between selecting facts from the library and proving more and more theorems using the right selected facts. It was purely syntactic. It was looking at the features of the mathematical objects, at the like symbols in the formulas. For example, you look at the conjecture you want to prove. You look at the symbols of it. You look at the symbols of the other things that you already prove, and then you do some sort of similarity metric based on the symbols. So that would be like very symbolic. Whereas what you can do also is to take as a characterization of a formula the set of models in which the formula holds. So you can, in what we are doing, when you want to prove a formula from some axioms, if the axioms are not sufficient, if they do not have sufficient logical power, you can very often find a countermodel, finite countermodel, that demonstrates that the axioms hold in that countermodel, and the negation of the conjecture also holds there. So that tells you this is a counterexample, and you cannot get through, like you will never prove this. So if you generate a lot of these countermodels, you can basically, for each formula, give it a characteristic vector of valuations in your finite models, because you can just evaluate there. Like imagine you have many different groups, and you have a group theoretical statement, and now you say, oh, in this group it is true, in this group it's false, etc., etc. And this is like a very different characterization of the formula, which I call semantic in this case, than the symbolic one, when you just take the parse tree of the formula, throw it to some graph neural network or whatever. It does some convolutions, but it doesn't have the chance to do the combinatorial thing that the model evaluators are doing. Like typically they are based on such solvers. So it's a very combinatorial task, especially if you have many quantifiers in the formula, to see whether the formula is true or false in the model. So you could try to learn it from the syntactic structure, and we actually are sort of trying it, but it's very difficult, like compared to the tools that are sort of targeted for this. So in general, you could say that whenever you have some smart technology based on some intelligent mathematics, like for example for groups or loops, you can have many advanced theorems telling you that, I don't know, a loop has some property, for example. So whenever you use this knowledge, I would use it, I would call it like a semantic characterization of your mathematical objects, rather than this sort of very straightforward, like syntactic, symbolic characterization of your objects.
So do you need to know about all